Okay, today we will discuss about semiconductor materials in this talk. Our focus will be on semiconductor optoelectronic materials, as the course being on semiconductor optoelectronics. What I have put here is a part of the periodic table, that shows group 2, 3, 4, 5 and 6 elements of group 2 part of it. There are 2A, 2B and so on, but don't worry about A, B, C and so on. Right now group 2, 3, 4, 5 and 6. The elemental semiconductors, the common elemental semiconductors comprise of group 4 elements. So, elemental semiconductors, first, the most common elements are silicon, germanium and also tin. All group 4 elements. As an element, these are semiconductors, which means the basic definition of semiconductor holds good: silicon, germanium and tin. We also have binary semiconductors or compound semiconductors. Binary semiconductors. These are usually either these are with one element from group 3, one element from group 3 plus one element, a compound formed by one element from group 3 and one element from group 5. Group 5. For example, if you see the table here, the elemental semiconductors are here in group 4: silicon, germanium, tin. The binary semiconductors are one element from group 3 and one element from group 5. The most commonly used elements are, or compounds are, gallium arsenide, one from 3 and one from 5, gallium arsenide. You also have aluminum phosphide, indium phosphide. All possibilities are there, one from group 3, one from group 5. So these are also sometimes called as 3-5 semiconductors. 3-5 semiconductors. Stable compounds of one element from group 3 and one from 4. You could also have one element from group 6, one element from group 2 and one element from group 6, forming what are called 2-6 compounds. 2-6 semiconductors. For example, mercury here and one from 6, cadmium telluride is a widely used semiconductor, zinc selenide or cadmium selenide or mercury selenide, mercury telluride are all group 2-6 semiconductors. So you may have 3-5 semiconductors or 2-6 semiconductors. What I have shown in the last row here, in this last row of this table, is the electronic configuration in the outermost shell of the element. For example, here mercury is there. Mercury's outermost shell has 5d10 and 6s2. It is group 2 because in the outermost shell there are 2 electrons. This is group 3. For example, This is thallium 6s2 6p1. All elements in this group 3 have a configuration in the outermost shell like 6s2 6p1 for thallium. For indium it is 5s2 5p1. If you go to gallium it is 4s2 4p1, and if you go to aluminum it is 3s2 3p1, and obviously if you come to boron it is 2s2 2p1. Boron has 5, atomic number is 5, which means there are 5 electrons. The electronic configuration is 1s2 2s2 2p1. Exactly like this, in the last column for all of these you can see that it is 6s2 6p2 for lead, but if you go to tin, germanium, the shell number reduces, but they have s2p2 configuration, which means there are 4 electrons in the outermost valence shell. In group 4 there are 4 electrons in the outermost valence shell, and therefore they form covalent bonds sharing 4 electrons with an adjacent atom to make an octet, that is 8 electron shell, which completes the octet. If you take one from 3 and one from 5, there are 3 electrons in the outermost shell here and 5 electrons in the outermost shell here, and therefore you again have the octet complete, 3 and 5. Similarly, in 2 6 we have 2 and 6 making it an octet. So the outer shell has an octet, which means it's a complete shell, makes stable compounds. So these are binary semiconductors. Typical, some of the binary semiconductors and their band gaps I display here. I hope you are able to read these. Gallium arsenide, band gap is 1.42 eV and lattice constant is 5.65 angstrom. Refractive index is given, approximate refractive index near the cutoff wavelength or near the band gap wavelength is also listed. So you can see some of the common binary compounds which are used: gallium arsenide, indium phosphide, indium antimonide, indium arsenide, aluminum nitride. These are the wide band gap semiconductors. Gallium nitride has a band gap here of 3.39 electron volts. This is nowadays, this is a very important substrate, gallium nitride, to get blue LEDs and blue lasers. It is the gallium nitride substrate which is used, indium gallium nitride. So indium nitride, what you see is also the numbers are listed to see that some of them have lattice constant 3 point something. These, the last 3 have lattice constants 3.1, 3.1, 3.5 angstrom as the lattice constant. But if you see the other common binary compounds like gallium arsenide, indium phosphide, they have 5.6, 5.8 as the lattice constant. This has some important implications which we will discuss shortly. So these are all direct band gap materials. The compounds that I have listed here are all direct band gap materials. I have a second list here. You can find these numbers in books and references. A common indirect band gap optoelectronic materials here: germanium, silicon, aluminum antimonide, aluminum arsenide, gallium phosphide, aluminum phosphide, and silicon carbide. Silicon carbide is also today an important material used for UV detectors. You see its band gap is very large, 2.42 electron volts, and lattice constant is about 3 angstrom. All of them have high refractive indices. As you can see, unlike the normal glass, most of them have refractive indices 3 to 4. These are all indirect band gap materials. Some of the common direct band gap and indirect band gap materials. Now, the choice of semiconductor for any application depends on the band gap. So this is the direct band gap material. Now, when we have so many semiconductors, how does one choose the required semiconductor? This is determined by the band gap wavelength or the cutoff wavelength. In optoelectronics, most of the material properties which are essential for the device functioning is emission and absorption. So it is the band gap which determines what is the wavelength that it can emit and absorb. So we have EV, EC, and this is the EG. If a photon is incident, a photon of energy h nu is incident on the semiconductor. So this is the semiconductor which has electrons and vacant states or some electrons there. Incident photon can be absorbed provided, if I call this as energy E1 and E2, then h nu must be equal to E2 minus E1. If an electron sitting at energy level E1 makes an upward transition to an energy level E2, then E2 minus E1 is equal to h. And therefore, the smallest energy photon which can be absorbed by an electron transition, by an interband transition, is h nu equal to Eg. That is the frequency or energy corresponding to the smallest energy corresponding to the photon which could be absorbed. Similarly, if there are electrons, large number of electrons here, they could make a downward transition, and the difference in the energy will be emitted in the form of photon. So this emits energy in the form of photon, and the smallest energy photon will correspond to h nu is equal to Eg. So if we write this as h c by lambda is equal to Eg, or lambda is equal to hc by Eg, and this is called the band gap wavelength. Lambda g is equal to hc by Eg. H is the Planck's constant, c is the velocity of light in vacuum, which are constants. So you can substitute values to this. If you substitute the values, then you find that lambda g in micrometers is given by approximately equal to 1.24 divided by Eg in electron volt. This is a very useful formula. The band gap wavelength in micrometers is approximately equal to 1.24 divided by Eg in eV. If I give you a material and say, all right, gallium arsenide has a band gap, so gallium arsenide has band gap equal to 1.42 eV. What is lambda g? The band gap wavelength, that is the smallest energy photon that can be absorbed is this, but in practice we handle sources with wavelength. We normally don't talk in terms of energy but in terms of wavelength, and therefore lambda g in micrometer is equal to 1.24 divided by 1.42, which is approximately 0.88 micrometer. So a quick estimate is given by this formula. 1.24 divided by 1.42, approximately 0.88 eV. Indium phosphide has a band gap of 1.35. Gallium nitride has a band gap of 3.39 or 3.4. So which photons, what energy photons it can absorb or emit, you can immediately find out. Gallium nitride, you don't need a calculator. Gallium nitride is equal to lambda g for gallium nitride. So lambda g for gallium nitride is 3.4 divided by 1.24, sorry, that is Eg. So, gallium nitride is 1.24 divided by 3.4 or 3.39, you can find out approximately. This is approximately equal to, how much is this? Approximately 0.35 or something, 0.36 micrometer. Please check. But this is a very useful tool. Instead of substituting H, which is 6.6 into 10 power minus 34 C, and then Eg you have to convert into joules, because 6.64 into 10 to the power of minus 34 is joule second H, and therefore you have to convert Eg to joules. But this is a very useful formula for engineers for a quick estimate of band gap. So, depending on the application, you have to choose the compound semiconductor. But we have a limited number of semiconductors, useful semiconductors, and therefore, if you want to continuously vary the band gap wavelength, or if you want to have materials with continuously variable band gap, then we go for the third type of materials that are called ternary compounds. So, first we have seen elemental semiconductors, very limited choice. Then we have binary semiconductors. When we have binary semiconductors, the choice becomes larger, because you can have any one compound, one element from group 3 and one element from group 4, group 5, and therefore your choice becomes wider. So, you have more number of useful materials. However, you do not have continuously variable band gap materials, and therefore the third type of materials are called ternary compounds. So, ternary compound. Ternary compound and quaternary compound. Ternary and quaternary compound. So, let me put back the table of elements here. In ternary compound, as name indicates, there are 3 elements, and in quaternary compound there are 4 elements. In ternary compound, we have 2 elements from group 3 and 1 from group 5. For example, gallium, aluminum and arsenide. So, from group 3 we have aluminum, gallium and arsenide. So, gallium, aluminum, arsenide. Or you can have one element from group 3. So, this is from group 3. They are still 3,5 compounds, but instead of one element we have 2 elements. So, how do we represent this? We represent this as AlX, gallium 1 minus X and arsenide, where X is the alloy composition. These ternary compounds are also called alloy semiconductors. Alloy semiconductors. What kind of values are used generally? X can lie anywhere between, so X lies between 0 less than or equal to 1. Usually X lies between 0.1 to 0.5, but in principle it could lie anywhere in this region. What does that mean? If you put X equal to 0, 1 minus 0 is 1, so we simply have gallium arsenide. If we put X equal to 0, the material is gallium arsenide. If you put X equal to 1, That means gallium is 0, we have the binary compound aluminum arsenide. So this is an alloy where X fraction of gallium atoms are replaced by aluminum atoms. X fraction of gallium atoms are replaced by aluminum atoms at the fabrication stage, at the formation stage. So these are called alloy semiconductors. Now, the importance of this can be seen in quaternary compounds. I come back to, let us discuss the importance shortly. I come to quaternary compounds. You can immediately draw an extension that it must be having 2 elements from group 3 and 2 elements from group 5. Indeed, you have gallium, indium, gallium, arsenide, phosphide. This is a very widely used material in optoelectronics and optical communication. Most of your laser diodes for optical communication are fabricated by this material, indium, gallium, arsenide. I could have this as indium and gallium from group 3. See the table. Indium and gallium are from group 3, and arsenic and phosphide are from group 5. So even the quaternary compound is from a 3,5 compound, but this could be written in this fashion, or it could also be, let's see what is the difference between these. Gallium 1 minus X and 1 minus Y and P Y. I mentioned that in the formation of aluminum gallium arsenide, X fraction, X could be 0.1, 0.2, 0.3, typical numbers are 0.1, 0.2, 0.3, somewhere in that range, 0.1 to 0.4 are the typical numbers, but in principle you can have any combination. X fraction of aluminum gallium atoms are replaced by aluminum atoms. Our starting material was gallium arsenide. Gallium arsenide is the substrate, and you have replaced X fraction of gallium by aluminum. So this indicates that gallium arsenide was the substrate. So the complete material system is very often indicated like this. Aluminum gallium arsenide oblique gallium arsenide, which means the starting substrate is gallium arsenide. Usually you start with a substrate, which is a binary compound, and then you get the alloys, aluminum gallium arsenide. What is the difference between these two? Here, what is the substrate, and here, what is the substrate? The substrate in this case is indium phosphide. We started with indium phosphide, X fraction of indium is replaced by gallium, and Y fraction of phosphorus is replaced by arsenic. Whereas in this case, the starting substrate was gallium arsenide. So the X and Y, 1 minus X and 1 minus Y, tells you which is the starting material. If X equal to Y equal to 0.5, then it is difficult to tell which is the starting material. So normally X and Y remain small. This is a quaternary compound, and so ternary and quaternary compounds are in general 3,5 semiconductors. It could be 2,6 also. We can have two elements from group 2 and one from group 6. In fact, zinc cadmium telluride or mercury cadmium telluride is a widely used compound. Mercury cadmium telluride. So that's a 2,6 compound. This is also a ternary compound. Similarly, you could have quaternary compound which are also 2,6. So you can have either 3,5 or 2,6. These are all stable compounds, stable semiconductor. Now the question is, why do we go for ternary and quaternary compounds? Or why go for alloy semiconductors? The binary are compound semiconductors, and the ternary and quaternary are in general called alloy semiconductors. Why ternary and quaternary compound? There are two important reasons. Let me write the answer first, that for band gap modification, and second one enables formation of or growth of this is the most important lattice matched heterostructures. Lattice matched heterostructure. It enables the formation or growth of lattice matched heterostructures. We will discuss the second point in the next class. Heterostructures, growth of heterostructures, design considerations, and lattice matching issue. Lattice matching means basically lattice constant of the compounds which are used to form heterostructures have to be the same, lattice matched. So we will discuss this later. First, let us see for band gap modification. As I mentioned, by changing the composition of, so let me rub this point, we will discuss that in detail. So for band gap modification, let's take an example and discuss what is this for band gap modification. If we take the example of aluminum gallium arsenide, which is widely used material, most of the laser diodes which are used in commercial products, laser printers, laser pointers, all music systems, CD systems, all use gallium arsenide, aluminum gallium arsenide laser diode, usually emitting at 780 nanometer, near infrared. This is in fact the most widely studied material. ALX, 1 - X, arsenide and gallium arsenide. So most of the commercial laser diodes, other than optical communication, as you know that optical communication takes place in the window of 1550 nanometer, not 780 nanometer, and therefore the material used is indium gallium arsenide phosphide, the quaternary material. Most of the devices are either based on indium gallium arsenide phosphide or indium gallium arsenide. So there are number of combinations which are possible, but remember that it's around 1550 nanometer, low loss window of optical fibers. And whereas most of the commercial devices use 780 nanometer, around 780 nanometer. And the material used is aluminum gallium arsenide and gallium arsenide. So depending on X, as I said, if you see the band gap variation, so what I am plotting is X, variation of X versus the material. So this is energy, Eg. At X equal to 0, which means we are at X equal to 0, it is gallium arsenide. So gallium arsenide. And at X equal to 1, we have aluminum arsenide. Gallium arsenide, all right. So we have to bring in at another concept, that almost all semiconductors have a direct band gap, indirect band gap. I am explaining the first point for band gap modification. If we plot the EK diagram or band gap diagram, for gallium arsenide, the band gap diagram looks something like this. This is E. The band gap here is, this is direct band gap, and this Eg is equal to 1.42 eV at 300 K. Usually the numbers that I put are at room temperature at 300 K. 1.42 electron volts. There is also a gap here corresponding to a stable minima here, and this is the indirect gap, and this is 1.90 eV. This is for gallium arsenide. Almost all materials have a direct gap and an indirect gap. The indirect gap could be here at the gamma point, and the direct gap could be elsewhere. The direct gap means the larger gap. All right, let me plot aluminum arsenide and then it will become clear. In aluminum arsenide, this is again E versus K for aluminum arsenide. This is for qualitative diagrams. Aluminum arsenide has an indirect gap here. This difference here is 2.17 eV. And this difference here is 3.02 eV. Please see this carefully. The point is whether I take gallium arsenide or aluminum arsenide, at K is equal to 0, there is a gap, there is a band gap, and here also there is a band gap. There is a minima here. Minima means that refers to stable states. Within this minima there are stable states, which means if an electron, excited electron comes here, it could come down and be stable here. So this is a stable point. So, but this gap is larger than this gap. This is an indirect gap, this is the direct gap. A material is called indirect band gap semiconductor or direct band gap semiconductor depending on which one of them is minimum. The smaller of the band gap determines whether the material is direct band gap semiconductor or indirect band gap semiconductor. So aluminum arsenide is an indirect band gap semiconductor because the smaller gap between the maxima of the valence band and minima of the conduction band is smaller here, which is indirect because that does not occur at K equal to 0. That is occurring at the minima, and the maxima and minima are at different K values. So it's an indirect band gap semiconductor. In the case of gallium arsenide, also you have an indirect gap, but the indirect gap is larger compared to the direct gap, and we say gallium arsenide is a direct band gap semiconductor. X equal to 0, we are here. X equal to 1, this will be the band gap. So, yes?
Will there be a local minima at K equal to 0 every time, or there will be?
Not necessary. The question is, will there be a local minima always? No, not necessary. Here you will have a local maxima, which is local minima for at k equal to 0, there is a gamma point, but this need not be there. There are materials where there is nothing here, means it simply passes like this. As you increase x, this diagram changes. So this gap, the new band gap does this. This is for x equal to 0 and this is for x is equal to 0.2. For example, as you increase x further, let us say 0.4, then let me increase this axis. As you increase to 0.4, they are almost coming at the same height here. This is for x is equal to 0.4. I am qualitatively explaining what is changing. When you change x, please see, when you change x, you are changing the environment in the crystal because you are replacing gallium atoms by aluminum atoms. The electrostatic field and the distribution there changes, and accordingly the allowed values of electrons change, which means the EK diagram changes with the composition of x. So as x increases, this is the situation. The direct gap has increased, the indirect gap has also increased, and they have become equal. After some time, when x is equal to I am going out of the board, x is equal to 0.6, this does this. What does that mean? So this is x is equal to 0.6, which means now the indirect gap is smaller compared to the direct gap, and this material has now become indirect band gap semiconductor. It was a direct band gap semiconductor. As you increased x, it became an indirect band gap semiconductor. So we have at gallium arsenide at x equal to 0 has a direct gap at 1.42 eV. There was an indirect gap which is 1.90 eV. Either I could have plotted this first and gave an explanation, or I gave the explanation and now I plot. Aluminum arsenide has the smallest gap 2.17, indirect band gap. So 2.17 is slightly over here, so 2.17 eV. And a direct gap which is 3.02, so 3.02 3.02 eV. Qualitatively, I am sure. So the direct gap here is going from 1.42 to 3.02 eV. This is the direct gap. The indirect gap is increasing, but slowly, and at this value of x here, around x is equal to 0.4, approximately around 0.4, that, so this is the, please see, so let me differentiate it by also having a broken line. What am I plotting? I am plotting the direct gap and indirect gap for the material aluminum gallium arsenide for different compositions x. So at any x, you just go up and see what is the direct band gap, what is the indirect, which one is smaller. In this case, direct is smaller. If you take an x here, 0.8, then indirect is smaller, direct is larger. which implies that this material is indirect band gap semiconductor. In this half or this portion, the material has become indirect band gap because the smaller gap is indirect gap. The direct gap is larger now, and therefore the material is indirect band gap. However, from x is equal to 0 to x equal to 0.4, it is a direct band gap material, and the band gap can be varied with x. By changing the composition x, I can continuously vary the band gap of the material. And that is the importance of aluminum gallium arsenide alloy. 1 minus x Is this clear? So, material has a direct gap, indirect gap. As the composition changes, the EK diagram changes. I have qualitatively shown how it is changing. It is increasing. Both of them are increasing here. But later this gap, that is minima to maxima, this difference is smaller compared to this difference, and therefore the material is indirect band gap semiconductor. So, in the range 0 to x equal to 0.4, aluminum gallium arsenide is a direct band gap semiconductor where the band gap can be continuously varied. We will continue from here in the next class. We have a quiz today. The other important material where also the composition is band gap is varied is gallium arsenide phosphide. So, gallium arsenide is 1 minus x and P is equal to x instead of aluminum arsenide. So, the starting point at x equal to 0 is gallium arsenide, and at x equal to 1 we have gallium phosphide. So, this is at x equal to 0, x equal to 1. This is another important material which is used to make all the visible LEDs. The red yellow LEDs are made by gallium arsenide phosphide, which is also co-doped with nitrogen for certain reasons. We will discuss that when we come to LEDs. But the principle and methodology of band gap modification remains the same. Normally, a quiz should not take more than 3 minutes. Maximum time is 5 minutes. And as you know, every quiz is for 1 mark. At room temperature, let me read the quiz. At room temperature, the energies corresponding to the band edges and the Fermi level of a particular semiconductor with MC equal to MV are given by EC is equal to minus 4.2 EV, EV is equal to minus 6.0 EV, and EF is equal to minus 5.2 EV. Question A, identify whether it is a P-type or N-type semiconductor. Give reason for your answer. Just one line reason. No detailed explanations. B, what is the probability of occupation of electrons at the conduction band edge? All the energy values have a negative sign in front. We will discuss why.